Okay, let's get started. Good afternoon all. So, a quick note about the last lecture. Maybe you have noticed the video uploaded on Canvas under Panotop has audio missing for about half an hour. So I was informed by the IT people that there was some wireless microphone issue, but that's okay. I uploaded that section from last year's Zoom lectures, so you can revise it from there if you need to. Well, that's actually a good example of the challenges in wireless, right? And it's ironic that it happened when we were learning about wireless and mobility. So I can talk here 2 hours explaining the challenges, but that's a good example on what can go wrong in wireless. So I don't know what exactly went wrong. Maybe it was scheduling problem. Maybe it was transmission problem, reception problem. I don't know. But there are many challenges we learned. It can be any of it. So starting from today, we'll be looking at multimedia networking. So you may be thinking, well, I know what media is. You have social media, you have classical media channels, but then what is multimedia? Well, multimedia is the form of all the forms of images, text, video, and audio applications that are put in a single interactive presentation. So you can view it, you can download it, you can interact with it, and so on. So these are the things we'll be looking at in this chapter. First, we'll be looking at some of the networking applications regarding multimedia. And in fact, in today's web, a lot of the traffic is in fact multimedia. Well, yes, we have web servers, we have websites, yes. But when you in fact look at the data rate in different web servers, I don't know, perhaps 90% of it comes from video streaming, voice over IP, or listening to some sound files over the web and downloading such files again over the web. So it's a huge part of the data networks today. So we'll be looking first at the video streaming stored video. Well, the main challenge is in streaming stored video is the bitrate. You must have a high bitrate. Well, why is that? Because in an image, you only download the bits for that image when you want to view an image on Instagram, let's say. But in a video, you have about 24 or 30 of these images in a second. So that's a lot of images. And on top of that, you have sound in a video, which is much smaller compared to the image, but still it occupies some data rate, some throughput. Next, we have the voice over IP applications. So this is applications like Skype or communication over WhatsApp, perhaps. We also have teleconferencing applications like Zoom. We're going to learn about some of the protocols, real-time transport protocol, RTP and SIP, to support these real-time conversational applications. And, these applications also matter in the way they are viewed. So it is different to view a stored video or a stored sound file, and it is different to view a real-time rendered video, such as a broadcast. If you're watching Twitch broadcasts or live YouTube videos, that is different. We have different challenges. Why? Because the time that video is recorded is just a few seconds before the users are watching it. So you have to take that video from that storing user, that rendering user, and then you have to distribute it to hundreds of thousands of users all around the world. And this has to happen almost real time in just a few seconds. Whereas in streaming stored video, some people shot a movie and then they stored it in thousands of CDNs all around the world. They had the time to distribute that, and now you're just entering the web, finding that CDN, that Content Delivery Network server. Don't worry about the names, we'll be learning about all those. And you just stream that video. So we'll see how each of these have different challenges, whether it be broadcasting, whether it be streaming, or be it voice over IP. And then we're going to be looking at how we can configure our networks to support these multimedia applications, what guarantees we can provide, and what are the things we cannot provide by just using TCP and UDP as transport layer protocols. Okay, so let's begin by a simple experiment to understand how much bitrate are we talking about in streaming videos. So let's say this is my monitor. So in today's monitors, if you have a full HD monitor, you have a 1080p monitor. That means you have 1080 pixels vertically, and you have 1920 pixels horizontally. I think this is what this monitor is. And if I'm watching a video, well, each pixel on my monitor has to display a small piece of that video, which is defined by the pixel on the monitor. So let's say this is one of such pixels. And let me zoom it here. This is one pixel. And if you look very closely to your monitor, you will in fact see that this pixel is divided into three. And if this is an LCD monitor, it will be represented by a red, green, and blue LED lights. And in the video data, the bits represent how much intensity each of these colors have. So if this is a red image, for instance, and let's say I have in total 8 bits to represent the intensities of each of them, if this is a red colored pixel, just like the ones I'm drawing here, that would have a high intensity for red. Maybe it will be 1111, 0110. It's not the reddest possible thing, but it's very red. And you will have very small numbers for the other ones. Again, it depends on the exact color we are talking about, but by finding different combinations of these colors, you can build a lot of colors. And this is how we, in fact, encode video in the simplest form without any decompression in the raw form into pixels to be displayed on monitors. And again, this is just one pixel. So in one pixel, I have 24 bits of information, right? 8 for the red, 8 for the green, 8 for the blue. Well, if this is an HDR video, I would have more, because that has more color intensity, more color diversity, and so on. But for normal monitors, for normal video files at least, that is 24 bits. But that is not all. I have 1920 times 1080 of these 24 bits. So that is the total number of bits I have in just one image of the video. But again, that's not all. I also have about 24 to 30 of these frames, images, in a video file. So that is, let's say 24, get the lower bound, 24 frames per second. So overall, this gives you your bitrate in a raw stored video file. Well, these are just experimental numbers. I mean, it will depend on the resolution of the video, of course. But let's just try to calculate this thing over a calculator. Okay, so that is 1920 times 180, right, times 24 times 24, and what's that? That's 1,200,000,000, right? So that's 1,200,000,000 approximately. Which is equivalent to, oops, which is equivalent to 1.2 gigabits per second. 1.2 gigabits per second. Well, that's a lot of bit rate. I don't know you, but I don't have this high bit rate in my home. But I can stream, let alone Full HD videos, I can stream 4K videos without any network issues. So how does it happen that when we write down the amount of data contained in a video file per second, it is 1.2 gigs per second, gigabits per second, but with an internet speed of perhaps 10 megabits per second, I can view such videos. Well, this is what we are going to learn now. So the first thing we'll look at is multimedia video, and we will learn about how to encode video, how to store them in web servers, and how to download them, how to pull them from the web servers, what protocols we use. So, as we all know, video is a sequence of images. Well, obviously there is audio as well, but that's a very, very small part of the data, so let's just ignore that for the time being. It can be 24 images per second, 30 images per second, doesn't really matter too much, but it's an array of pixels, as we just saw. And each pixel is represented by bits, perhaps bits representing different colors. And instead of storing and sending video frames in the raw form, we can use, in fact, encoding. So this is a way to reduce the amount of redundancy, the unnecessary bits in the video, without losing any or much information, much user experience. So it's something like this. Let's say I'm running a grocery store, and you are buying stuff in bulk from me, and you are buying, let's say, 1,000 apples and 500 oranges today. Instead of you telling me, I want to buy apple 1,000 times, and then orange 500 times, you can just tell me I'm buying 1,000 apples and 500 oranges, right? And the next day you're coming, you're buying the same thing. Instead of saying even 1,000 apples and 500 oranges, you will say just same. I'll buy the same. That's it. This is how you coded the information you're telling me. Well, we can do similar stuff in videos. For one, we can do spatial coding. So this is coding over space. Let's say this is the image in one of the video frames. So a man is running. And if you look at the sky, and this is the characteristics of many videos, usually the pixels next to each other are colored the same or very similar. This is all purple here. So instead of sending n values of the purple, and again, remember how we represent purple, it's bits, right? It's 24 bits for each pixel. Instead of sending that repeatedly, we just send that color and then say where that pixel starts and where that pixel ends. That's a very good way of spatial coding. So for each repeated value, you don't repeat the same pixel bits again and again. So this is spatial coding. The next method is coding between the frames, also called temporal coding or time-based coding. So typically in a video, the images don't move too fast. So if you're watching a man running in a film, the chances are in the next frame you'll still be watching that man running, because there are 30 frames per second, right? Or 24 frames per second. So if in the next frame that man is still running but moved very slightly in 1/24 of a second, you can just send the same frame, or almost the same frame, or you can just send the bits that are different from the earlier one. And that is temporal coding. So if you do both of these kinds of coding, and there can be other more advanced methods. For instance, now, it's not related to coding, but just an outside example. Now, with NVIDIA graphics cards, with the ray tracing and DLSS, I think it's DLSS mostly. So when you're playing games, the frames are rendered at a much lower resolution, and they are also rendered at a low frame rate. But then these frames are generated with AI, using AI, and then you can have a very high frame rate. And some of these pixels in your image can also be upscaled. So the AI engine guesses what these pixels should be. That's an outside example, but possibly in the future we can have these kinds of methods. So you can just store video at a very low resolution, you can send video at a very low resolution, and then the client device can, using AI, upscale that image and insert frames in between the images. Perhaps at 12 images per second you receive it, and you render it at 24 images per second. Again, this is not a technology that I know that exists today, but it might be possible in the future. But in today's videos, these encoding methods are definitely being used. No one wants a full HD video requiring 1.2 gigabits per second. So there are two broad classes of video encoding methods. One is the CBR, the constant bitrate. So here we are encoding the whole video using the same method, same amount of compression, same amount of redundancy removal. But we can also adjust the video encoding rate depending on the amount of spatial and temporal coding changes, and that is variable bitrate. So some of these examples are the MPEG-1 used in the earlier CD-ROMs and MPEG-2 used in DVDs. Just notice how the bitrate changes for the same videos. Higher bitrate means there is still some more redundancy, a little bit of less compression. But often in the internet, this is the format we use, MPEG-4, and this is variable bitrate. So we can adjust the bitrate depending on the requirements. If we can support very high rate videos, if the network allows it, if our storage allows it, we can encode video without removing too much redundancy, without too much compression. And if the network does not allow, vice versa. Yeah. And you know, in also in Zoom sessions or in video conferencing sessions, the video of the presenter person speaking or the screen shared screen image can also be compressed, but this time it happens on the fly rather than compressing first and then storing. The image is recorded by the camera, and then it is encoded on the fly depending on what the network can support. I think you also have seen that in Zoom videos, typically, if your network is good, you receive a good image of the speaking person, right? But once that network quality drops, you'll start to notice these rectangular pixels. The video image will be blurred. That is because it is using variable bitrate, and when the network cannot support, it goes to more compression, more coding. And again, why does the quality drops if we are coding this way, both temporal and spatial coding? Because these are lossy compression methods. So my eyes cannot notice, but probably, you know, the pixel here is a little bit different than the pixel here. The pixel on the right top is a little darker purple than the pixel at the bottom left. But if we encode both of them using the same color, assigning both of them the same colors, there will be some loss of quality noticeable by the user. That's why. Okay. Any questions about video? Okay. So let's go on to audio then. Well, audio doesn't require so much bitrate, but audio has its own challenges. So the problem here is that all natural sources of sound are analog. So be it humans talking, or be it the instruments in a concert, they are all analog sources, or the sources in the nature, they are all analog sources. The values, the amplitude of the sound waves can take any value. They can take continuous values. But in the digital world, when we are sending stuff over the networks, it has to be coded into bits and bytes. So we have to first sample these analog signals, and then we must quantize them. So here you see an example of that. So this blue curve here is your analog signal, maybe some human speaking. But to convert that, to encode it in bits, we need to take samples. So I take one sample here, 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 and so on. And each of these samples have their own magnitudes. So let's say I'm using up to 256 quantization levels. My values can take my quantization thresholds can take any values from 0 to 255, which can be represented by 8 bits, right? Because, 2 to the 8 equals 256. So I can represent all the numbers from 0 to 255 using just 8 bits. So in audio, if I'm using, again, 8 bits to quantize, I can represent each of these magnitudes using bits. So maybe this is, the first one is 185, the second one is a little higher. Maybe this is 194, the other one is 205, and so on. And again, think of these as bits. I can represent them in decimal format or bits format, doesn't matter. And after encoding, then we either store that audio file or we can send it over a network. So what affects our quality here then? Well, obviously, our sampling rate affects the quality. If you're not taking enough samples, especially for the high frequency waves, you might lose some information. Have you heard of the Nyquist rate? That is for the periodic signals. Our sound signal may not be a periodic signal, but as a generic reference, you want to sample at least twice the frequency of the highest frequency harmonic in your audio signal. So if your audio signal is a human voice, which is typically about maybe, 100 hertz for the bass sounds, like these guys who are giving speeches or maybe concerts, for some soprano woman, maybe it is I don't know, 4,000, 5,000, let's say 4,000 hertz. Maybe some people can go above that. But typically in a Zoom call, nobody will go like a soprano and go to 10,000 hertz, I think. So if that is our sound frequency, the highest frequency in our sound waves, well, typically we would like to sample at least twice that rate. So, you know, if you sample at 8,000 per second, 8,000 samples per second, which is the one used in the telephone, you can pretty much capture most sound waves without losing much. Again, I'm saying much because these are not periodic waves. Well, for CD music, the sampling rate is higher because the user demand is higher. Some audiophiles will complain if you sample at a lower rate. And even they won't be accepting CDs, they will be listening on gramophones. That is one cause of the loss, sampling rate being low. Another cause is the quantization levels. Well, obviously these 255 quantization levels will not give you the exact same wave when reconstructed, when the signal is reconstructed. So, as you see, all these points, when I draw them and send them to the destination will try to reconstruct the original signal, and the original signal will perhaps be a little bit different than the one that is reconstructed. And that causes a little bit of a difference between the original signal and the actual signal. So here our challenges are sampling and quantization and how to ensure the desired quality of the audio without compromising, without having to encode using too much bits, without having to require a very high bitrate. That is our challenge. I already explained, but so if this is your quantized value of analog value, that will be your quantization error. Again, so you encoded, you first sampled your audio signal, you assigned them quantization levels, and you can store them, you can send them to the receiver, and then the receiver again converts them back to an analog audio signal and plays it to the ears of the client. And some quality reduction may happen. So some example rates are this, because CD is sampling at a higher rate than the telephone, the bit rate is a little higher. And for MP3, it can be any of these things depending on the encoding format. For internet telephony, it is much less. Again, the main use of the telephony is for human sound, which is not varying, unlike other sources. And human ears can only hear between 20 hertz to 20,000 hertz. So this is an approximate gauge, of course. Some people can be higher, and as you get older, you hear a little bit less. So sampling rates above 4,000 bits per second don't add too much quality. Sorry, 4,000 samples per second add too much quality, because we can hear up to 20,000 hertz, and sampling at about twice the frequency, roughly, as a guide is good enough. And that's why we have much less bitrate in internet telephony. Okay, so these are, audio and video are two separate classes of applications, but we have a different way of looking at application types. So, first of all, we can be looking at streaming the stored audio and video. So this is, that data is recorded, that data is stored somewhere at a server. Maybe it is distributed to a lot of servers around the world, and then people are downloading that data, and then they are streaming that or listening to that. So the good thing here is that the streaming can begin play out before downloading the entire file. So this is also the buffers in video streaming platforms in YouTube or Netflix. Once you click on, even before you click on play sometimes, you see a very light gray bar filling up. So that is your buffer, and that can begin, your client device can begin buffering the video even before the playout begins. And if you can even view the video, and you can also listen to the audio even before downloading the entire thing. The computer is about to restart. No, I don't want that. And yeah, so the server can transmit faster than the rendering rate of the audio. This is again related to your buffer. If your buffer has enough size, your client device can download the video and audio files much faster first, and then even if later your bitrate drops, you can still display, your client device can still display the video that had been buffered earlier. And examples of that is YouTube, Netflix, and Prime Video. The second type we have is conversational voice and video, such as voice over IP or teleconferencing. So the constraint here is the interactive nature of the service. So in a call, we would like to hear the other party in maybe a few hundred milliseconds at most. If the delay is above that, there will be clashes. We thought the other party is not talking, and we'll start talking, but the other party had already talked, so the packets were on the way, but it has not reached us. So it's a very bad experience. I'm sure most of you have experienced that. So our performance constraint here is very low delay between that playout time and the time that file or that audio and video is recorded. And finally, we have streaming live video and audio. Well, that is somewhere in between the other two. So here, again, we have the interactive challenge. If someone is streaming in Discord or Twitch or even live concerts, we need to hear that. We need to watch that in at most a few seconds, maybe not milliseconds this time, not in the order of milliseconds. Usually the broadcasts occur a few seconds after they are recorded. We have a little bit of relaxation there, but the challenge is it's not one-to-one. It has to go to perhaps millions of viewers around the world. And that real-time challenge is making it very hard, because if you don't have enough time to distribute it to all the CDNs around the world, all the servers and data centers around the world, you have to do it in a very limited amount of time. So let me first explain how we represent the time they are being recorded and the time we want to receive them and view them. So I'll be using these kinds of graphs where we have the cumulative amount of data here. So in a video file, you can think of it as frames, or in a speech, in an audio file, you can think of it as audio chunks. And here you have time. And at the client side, at the server side or at the transmitter side, this will be our cumulative data. So it will be produced based on some function. Let's assume cumulative data increases linearly over time, so a constant rate of production, right? So the slope of this would give me the rate of production. And let's use another color here. Oh, my mouse disappeared. Ah, that's why. You know, you can warn me about this. Okay. And after some time, our client here will need to obtain this. And there will be some playout delay between the time it will be obtained at our client buffer and the time it is being played. Let's say this. So this is played. This is obtained. And this is recorded. So our constraints will change. So this will be called the playout delay. I'm just giving you some terminology here, so we'll be using these later. So in a conversational audio, obviously, this time frame between the time it is recorded and it's been played. Never mind. Oops, not that. So, if you're talking about an audio, that time frame from the moment it's been recorded and played is perhaps a few hundred milliseconds, right? We don't want conversational audio to be delayed too much. So, whenever we obtain, we don't really have much time until we play it. But for a video streaming service, such as Netflix or YouTube, assuming you're not streaming live videos, the record is far out in time, so it's been recorded much earlier, and this playout delay can be a little larger. I can increase this playout delay because, you know, it really doesn't matter too much if I start streaming the video 50 milliseconds after I click on the play, or 500 milliseconds after I click on the play. Maybe it matters if it starts 10 seconds after I play. I don't like that. I don't want to wait 10 seconds before watching every video. But maybe 1 second or 2 seconds don't matter too much. So it will depend on the application type. And one other problem is we won't be obtaining the video in a straight line like this, because our network delay will be variable. So instead of that blue line here, when we try to receive video, you will be receiving at variable rates like this. And if that variable rate crosses the time you are playing it here, you won't be playing this portion on time, correct? Because you haven't received it, you haven't buffered it, but now you need to play it, so your video stops or your audio stops. Or if this is a conversational video, you won't be hearing what the other party says. Any questions? I'll be using this kind of graphs for the rest of this chapter. Okay, now let's see streaming video over these kinds of graphs. So by far, the most important requirement of video streaming is the bit rate, or the average throughput, or the average bit rate. So here is what happens. Again, the same type of graph. On the y-axis I have cumulative data, and on the x-axis I have time. So someone recorded the video, and they put it in a content distribution, content delivery network, some data center, basically. And yeah, you see, so this video is recorded at 30 frames per second. So when you stream it on your PC, in every second there has to be 30 frames. So you can think of this as maybe 30, this is 60, and each of these is, 1 second, 2 seconds, 3 seconds, and so on. This is just one way to think. And then once someone streams that video is sent over the network, and the red plot here represents the time server starts sending the video. So the moment I request and my request reaches the server will start sending video. Let's assume the server sends it in the same rate, in the same bit rate that it's been recorded. So you see the same type of stepped graph with the same average slope. But my client device will not be receiving it at the same time, right? There will be some network delay involved. So my client device will receive it here. This is when I receive, and this is when the server sends. And this duration in between is called the network delay. And in this example, we have fixed network delay, but that's not always the case. So if I'm receiving the video a bit later than I requested, what I can do is I can just start streaming a little bit later, somewhere here perhaps. And this is when I would be streaming. I will have a graph like this. So as long as I stream only after I receive it, I'll be fine. I'll experience no freezes, no loss in the quality whatsoever. But again, in this example, the network delay is constant, meaning there is no network jitter, no delay jitter. So let's talk about our constraints here. So once the client playout begins, once I start playing my video, the playback must match the original timing. So that also means there must be no freezes. Otherwise, we are degrading user experience. But the problem is network delays are variable because there will be different amounts of congestion, right? And there will be different amounts of queues at different routers. Maybe in the middle of your video, your neighbors will also stream something, and then your ISP's links to you will be worse. So we must perhaps keep some buffer there before we play the video. So we start downloading, fill our buffer a little bit, and then even if the network delay increases, we can still use our buffers. So this is like in finance, in financial advice, you're always advised to put some money to the bank, right, for emergency situations. Let's say you are a salaried person, you're earning a fixed amount every year. Even if you are spending that all you earn, you are still advised to put a little bit of money in the bank so that if you get unemployed or something, or you get a pay cut, you still use your reserves. This is the same thing here. What other challenges are there? Well, the client can be, the application can be interactive. The client can fast forward the video, or the client can rewind the video, or jump through the video. I can click on second 5 while the video was streaming second 2, for instance. And we have to accommodate that. And, video packets may be lost, and they may require retransmissions. That would also add up to our overall throughput requirements. So let's revisit that example with a little more realistic graphs here. Again, the video is transmitted at a constant bitrate. Let's assume it's being transmitted at constant bitrate. But this time, the black plot here represents, again, our receiving time for each video frame. But this time, it's not as smooth. Because in some portions, like this one, the network delay is high, so we received it a little bit late. But in some other portions, we received it very quickly because the network performance is very good. Our data rate or throughput is higher. But overall, let's say our throughput, the average throughput, in other words, the average slope of our received plot, is higher than the transmission, or at least equal to the transmission plot. Then, if we allocate sufficient playout delay time, we can still stream the video without any interruptions at a constant rate. And this difference here between the time we receive and we stream is the client playout delay. And the difference between the parts we played and the parts haven't yet been played but stored in the buffer is called the buffered video. So here we have this much of buffered video, but here we have much less buffered video. But this is still the money in the bank. If our network performance goes bad, if our bitrate is down, we can still use the buffered video. But obviously, if our throughput remains low for prolonged periods, we will consume whatever we have in the buffer, and then we'll still experience a freeze. So we add this playout delay to compensate for the delay jitter, or the changes in the network delay. Any questions? Okay, so let's give out some numbers, some parameters to things that we discussed. Again, we have our video server, and it is sending over the video frames over a network. And at our client application, we have a buffer. That rectangular shaped thing is our client buffer, and it has a certain size, let's say capital B. And it will be filled at a variable rate. Again, what is this rate? That rate determines the slope of this black line, the average slope. Of course, it's not a continuous plot, but if you smooth it out, that would give you your fill rate, x of t. But our playout rate is obviously constant. We are always playing 30 frames per second, no matter what. So you can think of it like also a pool. Some sink is filling that pool at the speed of x of t, and some other sink or some other hole at the bottom of the pool is emptying water with a constant rate of r. And that pool has a certain buffer size, B. And the amount of water, or the amount of video frames in our buffer, is represented by Q of t, capital Q of t. That is also our buffer fill level. and it will go something like this. So it will, our buffer will fill up when our throughput is good. It will be emptied when our network delay is high and the throughput is low, and so on. Yeah, so as long as x of t is variable, we will experience a variable amount of frames in the buffer. So how do we establish relations between these variables then? Well, for playout buffering, the most important thing is the average fill rate of the buffer over time. So as long as your average x of t, which we represent by x of t bar, or just x bar here, as long as it is higher than the playout rate, if we allow sufficient playout delay, they will never run out of buffer, meaning buffer starvation. Having no frames left in the buffer is buffer starvation. But if our average x is lower than r, buffer will eventually will be empty, and you will suffer freezes in the video playout until the buffer again fills a little bit. So that brings us to a trade-off here. Well, after looking at these two lines here, then assuming the average x is larger than r, why don't we just choose a very high playout delay, and as long as our average fill rate is larger than the playout rate, we should be fine. But then the problem is there will be a larger delay until the user begins watching. So you open that website or application, and after you click on play, the user still waits some time until the buffer fills. So it's a trade-off between the user experience. Do you want user to stream the video immediately after the user presses the play? Well, you should set a very small playout delay, but again, that might be risky, because if your initial playout delay is not large, you will start playing the video without so much frames in the buffer. And increasing network delays or drops in the throughput might cause you to enter buffer starvation. So that's just a trade-off the streaming services need to consider, or the applications need to consider. Any questions? Okay, so now we are going to look at the actual protocols that we use for streaming. So for streaming multimedia, we have first the UDP as a transport layer service, or we can use HTTP over TCP, just like browsing web. We can download video files using HTTP requests and responses. Or we have a different version of HTTP, which we call dynamic or adaptive dynamic, dynamic adaptive streaming over HTTP, what we call also DASH. So we are going to be looking at these. So in streaming multimedia over UDP, let's start with UDP first. The server transmits the video at a rate that matches the user's or the client's consumption rate. So it is the same as the examples we have seen before. This rate the server is sending here is the same as the consumption rate. It's 30 frames per second. But that also means that our transmission rate is oblivious to the congestion levels. Well, that might be a problem, because if you have too much congestion, if you have a lot of network delays and drops in the throughput, you might want to send video at a low rate to prevent congestions, perhaps. You can choose to drop the quality of the video, perhaps. But UDP, streaming multimedia or UDP, is oblivious to that. But there is still a short playout delay up to 1 second to compensate for the network jitter. Again, as long as your average throughput is large enough and there is not too much jitter, you won't be experiencing freezes. And I also said that the client might want to interact with the application, right? The client might want to rewind the video or choose a particular time to play the video from. So for those, there is a separate connection in streaming over UDP. So for these client comments to go to reach the server. So that is an out-of-band connection for that out-of-band control connection. And this is defined as the RTP protocol, the real-time transport protocol. Again, we'll be looking at that later on for multimedia payload types. This works over UDP, so you can think of it, although the name again is a transport protocol, real-time transport protocol, this works over UDP. So the UDP transport layer, the UDP packets encapsulate RTP payloads. So this is typically used, this UDP for multimedia is typically used in live video sharing. Because in the live video sharing, the latency constraint is very tight. The live streamed video needs to reach other clients in at most a few seconds. And UDP is a faster protocol than TCP because it doesn't have retransmissions. It doesn't lose time with retransmissions. Now imagine that some packets, some frames reached us too late in a video, but by the time our video needs to play the frames that come later than that frame. Well, in a video, do you actually perform retransmissions and then play those earlier frames? I don't think so. The videos are always continuous. The videos don't go back. So if we miss certain frames in UDP multimedia transmissions, we just miss them. The client application won't display them and will skip them. It doesn't have retransmissions unlike TCP. So it's the best effort service. It's commonly used for live streaming, live multimedia applications. But for stored video, it is not the choice. And another reason it is not the choice is the UDP may not go through firewalls. Some firewalls might block it. Okay. So the next application layer protocol we have for streaming multimedia is what you all know very well, HTTP. So this is the web's application layer protocol again. And just like getting an object from a web server for retrieving multimedia, again, we use HTTP GET requests. And then the video will attach in its response, in the body of the response, the video file in certain in some encoding format. And then our client application will receive it. So let me explain this figure. So on the left, we have the server. And the server holds a certain video file. Perhaps this is a Netflix CDN. And it has a send buffer. And it goes through the network. And on the right side, you have your browser. You can browse Netflix or YouTube on your browser, or it can be your Netflix or YouTube application, again on your phone or on your PC. And here our client application reads data from its client socket and places these bytes into the client application buffer. Let's say this is maybe the Netflix application. So you have a transport layer buffer, the TCP receive buffer, and you also have a buffer for your Netflix application. And the server also has a TCP send buffer. Here, unlike UDP's constant transmission rate, the server can send the video at a faster rate. So it is no longer this, but if the network allows, the server can send a lot at first until our buffers are full, and then it can send a lot. What's going on? The server can send a lot and then can send more if the buffer is full. So we can send at a higher rate than the video is stored or to be played. But still, both because we have a different send rate and we have a variable rate our client buffer fills, these fill rates, all of these fill rates will fluctuate. Also, TCP's congestion control might also cause these variable fill rates. If there are congestions, if there are retransmissions, some of the transmissions may need to be repeated. And you all know that in TCP we have in-order delivery, so if some frames do not arrive, we will still try retransmissions for them, and then the TCP window will move on. Well, the same as before, if we have a larger playout delay, obviously we have a smoother experience because there'll be a smoother TCP delivery rate. And here we have buffering, but in addition to buffering, we also have prefetching, that is sending the video frames at a much higher rate than they can be played, if the network allows, obviously. Okay, any questions here? Okay, so previously TCP was not the preferred choice in video streaming because people thought that these retransmissions, the congestion control and reliable deliveries are not really necessary, and it is hard to provide retransmissions in networks limited with throughput. But over time, people learned that, of course, this was also facilitated by the development of higher throughput networks. Over time, people learned that TCP's reliable transfer does not necessarily prevent us from building applications that are streaming video over TCP, and now this is the most preferred choice, at least using TCP is the most preferred choice when streaming stored video. Again, for live video, it's not, but for stored video, this is what happens when you watch videos on YouTube, Netflix, Amazon Prime, and so on. Again, this prefetching here is the key. We can send it at a very high rate when the network allows. So my question to you then here is, what happens to the server's sending rate? What was the variable name for that? We don't have the variable name for that. So what happens to this send rate when the TCP receive buffer is full? This is full. It's not a trick question. Well, the server will simply stop sending video frames. That's it. So this HTTP GET request also supports repositioning of the video, rewinding of the video, and so on. So let's say you want to jump from one part of the video to another part. In the HTTP GET request, your browser or your client application will indicate the video chunks requested. So perhaps that is get Netflix. I'm making this up. You don't get it from the Netflix server, but Netflix / byte range 255 to 284. It won't be looking like this. I'm just giving you here a mock example. But in the HTTP GET field, your browser can indicate what bytes, what chunks of the video it is requesting. So you do not need a separate out-of-band communication channel between the client and the server. You can use the same HTTP request and response sequences for getting bytes of the data out of order. Okay, so HTTP streaming is good, but there are still some shortcomings to it. So the video is stored in one format, and all clients get the video in the same format. But we also learned that different users might have different network experiences. Some of the users can be mobile, some of the users can be wireless, and some others can have broadband connections with very high throughputs. And HTTP streaming does not tailor the video rate to their bit rates or delay experiences. That's why we have a protocol built on HTTP called Dynamic Adaptive Streaming over HTTP, or simply DASH. So here the client application, depending on the network performance, will choose where to download that video frame, at what rate to download that video frame, and so on. So here each video is encoded into several versions. It can be a high data rate version, medium data rate version, low data rate version. In fact, I think in Netflix it's also like that. You choose the quality of the video, or in many many streaming services, you choose the quality of video from the right bottom corner, right? In YouTube, you select the resolution of the video. That is because that video file is recorded in different formats and stored at certain content delivery networks. And your browser can choose, if you select auto, it will be automatically selected based on your bitrate. It will select highest possible bitrate encoding of the video supported by the network. But you can also choose on your own. So video is encoded in different chunks. Each chunk is encoded at different rates, and obviously different rates have different quality levels. And there will be a manifest file which provides the URLs for all the different versions. So it will tell, do you want the low quality videos? You know, here is not the IP address, but here is the server you can download from, server 1, server 2, server 3, and so on. Do you want the medium quality one? You go to, again, you have it in server 1, you have it in server 5, and so on. And of course, within each server, it tells you how to address those files under what directories, what are the file names, and so on. So this manifest file is like the list of all different versions of the video file encoded in different bitrates. And the client here periodically measures the server-to-client bandwidth. And by consulting the manifests, it requests these video chunks, and it chooses the maximum coding rate sustainable given the current bandwidth. It can also choose different coding rates at different points in time, depending on the available bandwidth at different times. So if, let's say that user has a 5G connection and traveling on a highway, but then that car enters a tunnel, so suddenly the quality of connection drops to 3G, and the client application can switch by consulting the manifest from high bitrate video to low bitrate video. Even across time, for the same client, we can switch between versions, different encoding versions. So in a way, Dash allows a client to adapt to the changes in the network quality. So with Dash, we say that the intelligence here is at the client side, intelligence at client, because the client requests the manifest file which lists its options. It requests when to request the chunk. So depending on how much data is in the buffer, if there's too much data in the buffer, maybe it delays the request of the chunk. Or if the buffer is almost starving, it maybe requests a lower resolution version of the chunk. It also chooses the encoding rate in addition to when to request. We also already discussed this. And it also chooses where to request the chunk. It can request the chunk from URL servers that are close for less delay, or it can choose those with a high bandwidth to itself. So, let's step back and think about this fundamental question of what kind of a system we need to be able to stream these videos to not to just one client, but to potentially millions of clients simultaneously streaming that video. So manifest file is like a catalog you give them, and it tells them where each video file is stored. So obviously, you know that we are not using option 1, which is a single large mega server. By the same principle of the internet, not putting the complexity at the core, but putting it at the edge, putting the complexity at distributed levels, at various levels at the edge of the network. We do not want to use this mega server option. It gives us a single point of failure. What if the links to that mega server gets congested? And where are you going to build this server? If you build it here in Singapore, what are the users in Europe or US are going to do? They will have a very long path to that server. So obviously, we all know this is not a good solution. It doesn't scale. The second solution, the second option, and this is also the approach being used in practice, is to build a large distributed infrastructure to store and serve copies of videos at many different locations, thousands or tens of thousands of different locations that are geographically dispersed. And we call these geographically distributed servers the CDNs, content distribution or content delivery networks. These are in fact data centers. They store data like video and audio data, but they also have very high throughputs. And we have them at various points in the network. There are two major approaches to do this. One is to enter deep in the networks. So Akamai is an example of that type of network CDN provider. It pushes the CDN servers deep into many access networks. So these are at the levels of ISPs. So even within the StarHubs and SyncTubs network domains, we have so many Akamai servers probably. And because they are at the level of ISPs, your path to them is not usually congested. They are very close. You experience very low delays. Another option here is to bring home option, Well, this is not as deep as the first option, but here we have a certain amount of large clusters, which we also call POPs, or points of presence. So these are just group of routers in the service providers network. So you already learned in the first chapter that there are customer ISPs and the provider ISPs, and the customer ISPs are getting service from these provider ISPs at certain locations, and these locations are POPs, or Internet Exchange Points. So these CDNs are at the level of these POPs, but not within the access networks, not within the customer ISPs networks. So they are a little bit farther to you, not as close as the first method, but they are still being used because they have lower maintenance cost. You have larger clusters of a less number of CDNs. So there is a little bit of less management overhead, less expenses, and so on. But the user experience is, of course, better in this one, in the Enter Deep method. For instance, Netflix also uses, at least it used to use, Akamai servers to be as close as possible to the customers. And Google uses, or Alphabet uses, its own CDNs. It doesn't use any third-party CDN, at least for most of the services. Perhaps for some services, they have a lot of services that I don't know about, so they might be using third-party for some of them. Okay, so let's see a concrete example of how CDNs operate. So here our customer Bob is requesting a video from this first link here. And let's say this with.net Cinema is a streaming service like Netflix. This is not Netflix because this is not the exact approach used by Netflix. We're going to have our Netflix example later on. But let's say this is just one provider similar to Netflix that operates in a different way. So Bob goes to that netcinema.com website, and by this directory he chooses a particular video on that web server. Here we have netcinema.com server, and we have the authoritative DNS of netcinema.com. So the first thing is Bob gets the URL for the video. This perhaps happens by clicking on a certain video in that website. And then, well, here obviously I'm assuming that the Bob's local DNS or the Bob's browser knows the IP address of netcinema.com. Otherwise, this will incur a call to NetCinema's authoritative DNS. But let's assume it is already known. Oh, okay, it is not already been known. Okay, forget what I said. So, obviously, okay, in this example, Bob's browser doesn't know the actual IP address, so it requires name to IP translation through its local DNS. So it asks its local DNS, hey, what is the IP address of with.netcinema.com? And let's assume local DNS has not cached that information, so it consults the NetCinema's authoritative DNS server and obtains that the file, in fact, is stored here. Okay, yeah, I wasn't wrong actually. Sorry about that. So here we assume that Bob knows netcinema.com's IP address and directly gets netcinema.com's IP, and from there it will go to DNS server to resolve this address, and Bob's local DNS will return from NetCinema's authoritative DNS the CDN server that netcinema.com uses. And in this example, netcinema.com is not storing that video file on its own servers, but it is using third-party content distribution networks. That's why NetCinema's authoritative DNS told the local DNS that you can obtain that video file in this kingcdn.com. Now, in the DNS chapter, I told you that DNS performs multiple actions, multiple services. One of them was name to IP translation. Another one was for canonical names. You know, enterprise.com is in fact www.enterprise.com, but no matter what you enter, that conversion is stored at the DNS server, so you can make queries, and by CNAME records, you will still get the same IP address. Another one was what? Another one was for mail servers, right? Name resolution for the mail servers. And there was a fourth one. Anybody remembers what was the fourth one? There was another service that DNS performs, and that was a very key service, critical service for the operation of the CDNs. Anybody remembers? Okay, that was load balancing. I said DNS performs load balancing service in the internet, and here we see that in action. So Bob's local DNS then goes to KingCDN's authoritative DNS server, because it doesn't know this A1122.kingcdn.com's IP address, so it goes to the KingCDN's authoritative DNS and obtains the IP address of one of the servers in the KingCDN domain that keeps that video file, that stores that video file. Just one IP address within the KingCDN domain, which is a KingCDN server, kingcdn.com, and obtains the IP address of that and informs Bob, and then Bob requests the video from that KingCDN server. So, here in this example, this KingCDN authoritative DNS server performed a load balancing action. How so? This KingCDN has so many servers around at the level of ISPs, perhaps. This is server A, there is another one here, server B, there is another one here, server C. Well, maybe in this case, server B and C were occupied, they are facing a lot of users, or they are far from Bob. So Bob's experience would be bad. So this KingCDN authoritative DNS server picked server A and sent server A's IP address to Bob. Not server B's, not server C's. This is load balancing act in action. Any questions here? But then, how does that DNS, authoritative DNS server of KingCDN select the good CDN node? How does it know that A is good? Well, for one, it can pick the one geographically closest to the client. Well, if you ask me, how does it know which one is geographically close? Well, each local DNS is usually registered in a geolocation database. So depending on where Bob's local DNS is, it can estimate how far Bob is from each of these CDN servers under KingCDN domain. Another option is to pick the CDN node with the shortest delay to the client. Well, how can we do that? Well, in TCP handshake, this is using HTTP, right? So it has to use TCP. We have the SYN, SYN-ACK, and ACK. correct? The server can measure the time between these two, between the SYN ACK and the ACK, to get an estimate of the delay between Bob's client device and the CDN server, between this and between this. But that's not the whole story, obviously. If Bob didn't even try B and C, how does it know that A has the smallest delay? This entails the King CDN authoritative DNS server to redirect Bob to other servers, other CDN servers from time to time to get an estimate of the network delay between Bob and each of these servers. So a little bit of a trade-off here. So if we want to measure the delay, we want to try Bob downloading files, at least establishing a TCP connection, sending a ping to each of these CDN servers, ABC, to see which one has the lowest delay. So this is the second method. And in the third method, we are just letting the border gateway protocol handle it in IP Anycast. So in the internet, the routers usually route the packets to the closest cluster. And if King CDN assigns the same IP address to all of its CDNs, the Bob's client device will be routed to the one closest to it, because the gateways, the border gateways, will have routing tables, and they will typically route you to the IP address to the through the closest route. So that is just letting the border gateway protocol handle it. Okay. So I know this is just too much detail, so I'm just covering these to leave no questions, confusions in your mind. So if I just tell you that we are selecting the best server, this DNS is performing this load balancing by selecting the best server, then the immediate question that comes to mind is, well, how does it know what is best? And these are the ways to know what is best. Finally, we can, of course, let the client decide. We can give the list of CDN servers the client can choose from. So in this response, perhaps, the King CDN server can tell all the IP addresses of all the name to IP resolutions of all the CDN servers, and Bob's client application can select it. Bob's client application can ping servers if it needs to, and chooses the best one for itself. And there is also this Netflix approach, but I think we don't have time for that today. I'll go through that in the next class after giving a quick revision of what we learned about. Any questions? Okay, then see you next week. Have a nice weekend.